Hey everyone, welcome back to my Calculus 2 series. In today's lesson, we're going to be talking about work. So before we start, let's have a quick refresher of maybe grade 11 or 12 physics and Newton's second law of motion. I'm not going to go in depth as to what it was, but basically from the second law of motion, we kind of got this formula derived from it, which was F equals m times a, and I've kind of listed off what each of the variables there are. But essentially, the Newton's second law of motion told us that force was equal to the mass times acceleration. So now moving on to work. As you can guess, work probably has something to do with this formula with force. Otherwise, I wouldn't have told you to kind of remember that formula. So the formula for work is force times distance. And there you go. Again, I have labeled the variables over here just under the formula itself. But if we grab a closer look at the formula assumes that the force is going to be held constant, and that we're going to be able to just calculate the work on that interval, which is d, right, for like a certain amount of distance. But the problem arises when the force isn't constant, meaning that over certain distances we have sort of different amounts of force being applied. And so how do we go about calculating something like that? So let's think about deriving a formula for work when work is not constant, meaning it's variable on some sort of distance, right? So let's pretend that we have this interval right here, right? And then along that interval we have maybe like 3 sections, right? In this section we have force 1, in this section we have force 2, and then in this section we have force 3. So along all these 3 different distances, we have different forces being applied, right? In this case, the way we would calculate work is, well, we would just take the force of the first interval and multiply it by, let's say this is d1, this is going to be d2, and then this is going to be d3. We'll take d1 and multiply it by the force on 1, and then we're going to add on the rest of the intervals of work. So this is an interval of work, this is an interval of work, and this would be an interval of work. So we would just sum up all of these separate intervals, and then we would get the total amount of work that is done on this entire interval. So we can kind of scale this example and derive a more general formula for work. So essentially we're going to say that, okay, work at the ith distance, sorry, that might not look like an I. There it is. Work at the ith distance. Well, that is basically going to equal to f of xi times delta x. And I'm quickly going to go and define what each of these variables mean. So there you go. Basically, wi is going to represent the work done at the ith interval. So kind of like this entire piece, like all of these pieces would in a sense be wi. This would be maybe w1, this would be w2, this would be w3. And then f of xi, well, in this case we used capital F. However, I want to represent it more as a function. So I'm going to say f at xi, meaning at a certain interval, at the ith interval specifically, it's going to be the force, and then we're going to say that delta x is going to be the distance. So if we can calculate the distance at the ith interval, all that's left to do is to sum up all of these intervals like we did in this example right here. So we can therefore say that, okay, the total work done on the entire interval is going to equal to the sum, again from 1 to n, of f at xi, meaning the ith interval, delta x. So this will sum up all the intervals from 1 to n, but we kind of haven't defined yet what n is. And again, like in most cases, we want to take the limit as n approaches infinity so that we can have maximum precision, basically having as many intervals as we can have so that we can calculate this work like very, very precisely. And now if we look closely, well, this right here literally looks like the definition of an integral. So there we go, we've kind of derived the formula for work, and essentially all it is it's leading us back to this formula. We basically want to integrate the work function from a to b. So here's an example problem, and we can use the formula we just derived up here to solve this type of problem. So the question asks us, when a particle is located at a distance x feet from the origin, a force of x squared plus 2x pounds acts on it. How much work is done moving the particle from x equals 1 to x equals 3. So again, we know that the total work is equal to the integral of f of x. And f of x, if you remember, in this case, we've defined it to be the force of the ith interval. And in this case, it's telling us a force of x squared plus 2x. So that is the force function. That is the function that we are going to need to integrate. And then all that's left to do is determine the bounds of integration. But it's telling us the particle is moving from x equals 1 to x equals 3. So it's pretty simple over here. And obviously we're going to be integrating with respect to x, so we keep this dx. And now, I'm sure you've seen this integral plenty of times, so again, I'm going to zoom through this and we'll just get down to the final answer. There we go, and we have computed the total amount of work that is done moving this particle from x equals 1 to x equals 3. So it's a pretty easy example. All we needed to do was we needed to determine what is the force function, and then we just want to integrate it from the lower bound, which is given to us, to the upper bound, which is also given to us here. So now on to the final example, and as you'll see, this one's a little bit more trickier. However, once we go through the solution, you'll see hopefully that it's a little more intuitive than you think. So the question tells us that a tank has the shape of an inverted circular cone with height of 10 meters and a base radius of 4 meters. It's filled with water to a height of 8 meters. Find the work required to empty the tank by pumping all of the water to the top of the tank. So I like to start off these questions by kind of drawing myself a visual of what's going on, what they're trying to tell me, and then from there we can start slowly working towards the formulas that we're going to need and then the solution. So there's my little drawing. Again, sorry, I'm not an artist. It might not look great. However, I think I've portrayed the problem pretty well in a diagram. So the question tells us that we have an inverted circular cone, which is exactly the shape that I've drawn. It has a height of 10 meters, which I have labeled right here. And it has a base radius of 4 meters, which I have labeled right here as well. So again, it's a radius of 4, meaning this entire thing is going to be 8. The diameter is going to be 8. And then the question also tells us that we have water filled up to 8 meters. So I have marked the 8 meter point. Sorry if it's not to scale, but it's just kind of to get like a visual sense of what's going on. So the question tells us to find the work required to empty the tank by pumping all of the water to the top. So essentially we're going to have to take all of this water and we're going to have to pump it to the top. And again, we know that it has a height of 10 meters, so the water all the way at the bottom down here, well, that's going to have to go up 10 meters. So now let's start kind of working towards the formulas that we'll need and slowly stepping toward the solution. So the question asks us to find the work required. So the work, we know the work is equal to the integral of f of x, and then we want to use, this should be b, so it's equal to this, right? But this is a little too much for us because we're not yet given a function to integrate. So let's kind of step away from that and let's figure out how we can break this problem down. My proposal to you is that we break this problem down into intervals like we've been doing with everything, and that integral calculus is kind of good at. So we're going to break this right here down into each interval. And you see I've kind of drawn this blue like circle right here, but essentially that is going to be one layer of water. And we want to figure out how much work is done lifting that water all the way up to the top, right? So we are going to work on finding that. And essentially I'm going to say that this is Wi, and we know that the work is equal to force, the ith force, times distance, right? So now we can start kind of breaking down the little pieces that we need. So for the formula, we need a force and a distance. Okay, so let's start off with Fi. Well, what is the ith force equal to? Well, the ith force from Newton's second law is equal to the mass, the ith mass, times the acceleration, right? And now let's take a look at what this formula needs as well. Well, this formula needs a mass. What is the ith mass? Well, we don't know what the ith mass is yet, so we need to figure that out. So the mass at the ith layer is going to equal to the density times the volume. But now, do we know the volume of the ith layer? Not quite. So let's figure out what the volume is. Now, from previous videos, we're going to know that the volume, well, that's equal to the area times the width or depth in this case. And so we've kind of broken it down to, if we see the volume, well, the volume is talking about this shape right here, all of this shape, right? What is the volume of that shape? We're trying to figure this out for the ith layer, so we want to figure out the volume for this ith interval, or in this case, it's just going to be this little like cylinder. So how can we figure that out? Well, we've kind of done this before. What is the area of the base of this thing? Well, it's just a circle, right? So the area of this circle, so let's write area, it's equal to pi r squared, right? However, what is r in this case, right? What is this radius? I've kind of labeled it in black. Maybe you can't see, but I will outline it in red right here as well. What is this radius? One of the ways that we can figure out what the radius is by kind of using similar triangles. So we can see that I've drawn this little black dotted line, like this black triangle that we formed over here. And this is essentially the larger triangle. So we know that the height, this thing right here, is going to be 10 because that's the height of the cone. So the ratio over here is going to be, actually I'm going to put it this way, it's going to be 4/10. So it's going, the ratio that I'm going to write is this radius to the height. Okay, and now if we look at this triangle right here, I'm going to mark it in dark black. Now if we look at this triangle, well, now let's express that radius and the height, right? The radius is going to be here, and that's what we're actually looking for, so we're going to leave it as r. But what is the height? Well, the height, we don't exactly know where this layer is going to be located, but the height, if we've labeled as 0, the height is going to be x units upwards, right? So we don't actually know where this ith layer is. I've kind of just drawn it in the middle, and I haven't given it really like a x coordinate of where it is, but we're going to say that it's x unit upwards because we don't know where the ith layer is. We want to kind of generalize as much as we can. So we leave this as x because it's x units from here. Obviously, if you were to label this a little differently and say that, okay, this was going to be 10, this was going to be 0, and then this was going to be 2, if you were to label your graph like this, well, then you were going to have to say that this x value is all of this, right? Meaning it is going to be 10 minus x. This little portion is going to be 10 minus x. So now instead of writing x over here, you would have to put 10 minus x. But I've intentionally labeled starting from 0 here, 8 here, and 10 here. So that way this little distance would be just labeled as x because we're starting at 0. So now we've expressed the ratio of this really large triangle right here to this smaller one right here. Now we can go on to solve for what the radius is. All we need to do is we kind of need to isolate for r. So r is going to equal to 2/5 times x. Essentially, I've just cross multiplied and reduced it. So this is what r is equal to, and we have finally figured out what our first variable is going to be, and now we can plug this in for our area. So our area is going to be pi 2/5 times x squared. Again, we can simplify this to say that it is 4pi/25 x squared. And there we go. We have figured out the area of the ith layer right here. So this is just the area. This is just the top, right? But now, what is the volume of that ith layer? Well, if we look over here, right, we figured out the area, and all that's left to do is to figure out the width, or kind of the height of this little cylinder over here. And as you can see, I've already labeled it as delta x, so it's pretty obvious that, well, the volume is going to equal to 4pi/25 x squared delta x. There is our volume. I'm going to bring, let's say, this formula down here, and we've said that mi is equal to density times volume. So we have finally figured out, I'm going to leave this as d. We have finally figured out what the volume is. Now what's left to do is to figure out what is the density. And sometimes, actually a lot of the time, the question will tell you what the density is, but in this case I know that the density of water is equal to 1,000. I'm not 100% sure of the units, but we're kind of disregarding the units in this case. So it's going to be 1,000 times 4pi/25 x squared delta x. Now I can obviously go on to simplify this a little bit by crossing these out. So this will just be equal to 160 pi x squared delta x. and that is the mass of the ith layer. We have figured this formula out now. So now that we figured out the mass, we can start figuring out what the force is for the ith layer. So let me go ahead and write it over here. We said that force at I was equal to the mass of the ith layer times the acceleration. So the mass in this case was 160 pi x squared delta x. And we want to multiply this by a. And the acceleration that would be acting on this ith layer of water would be gravity. Gravity is 9.8 meters per second squared. So what we're going to have here, we're going to be ignoring the units, so don't really worry about them. We're going to have 9.8 times 160 pi x squared delta x. And if we go on to simplify, this will be 1568 pi x squared delta x. So here we go. We have figured out what the force for the ith layer is, and it's important that the ith layer is arbitrary, meaning we don't really know what it is, and we've kind of left it up to choice by using this dynamic sort of distance, by saying we don't know what the distance is, it's just going to be x. So again, now we figured out f of I, and now we can plug f of I into here and figure out the work done at the ith layer. I'm going to write the formula down here. The ith work was equivalent to the force of the ith layer times the distance that layer has to kind of travel, in a sense. So we have figured out what the ith force is. It was going to be 1568 pi x squared delta x, and now we want to multiply it by the distance that this layer, that this sheet right here of water, all of this has to travel. If the sheet, let's say, of water is all the way at the bottom, in order to dump it all the way to the top, well, it has to travel a total of 10 meters, right? But if the sheet is at position X over here, let's say, well, how far does that have to travel? So the way I figure this out is, let's say the sheet is at position 5 over here. How far does it have to go? It has to go up 5 units, right? Let's say the sheet is at 8. How far does it have to go? It has to travel 2 more meters. So obviously we can see that the expression for this will be 10 minus x. So the sheet of water, like this layer of water located at position X, will have to travel 10 minus x units to get all the way out of this circular cone. So now we go back, and now that we've figured out an expression for the distance, we just multiply by it. And now as you can see, we get this big expression going on over here, and this is the work for the ith layer. So now that we've figured out the work at the ith layer, all that's left to do is to sum these up by using an integral. So now that we have this integral, all that's left to do is figure out these bounds. So what are these bounds? If we think about it, these bounds, they represent where the water is kind of spanning from. So in this case, the water spans from x equals 0 all the way to x equals 8. And again, if you chose the scale to be kind of inverted, if you chose 0 to start here and 10 to be here, well, then you would have from 2 right here, this would be 2, the water would span from 10 to 2, so your bounds of integration would be slightly different. But in this case, because we chose to define the scale starting from 0, that means that the water will span from level 0, which is all the way here, all the way to level 8. So the bounds of integration will be 0 to 8, and we want to integrate this function right here. So now this is a pretty simple integral. As we can see, this is a constant. We can just move it outside of the integral, and we'll just be left with the integral of 10x squared minus x cubed, which is a pretty easy integral to solve. So I'm not even going to go ahead and bother with the solution. I'm just going to go ahead and tell you what the answer is. This is what the answer would be. So it would be 3.36 times 10 to the 6 joules. And yeah, now we can see how we have kind of applied everything that we've learned, several different formulas, to figure out what the work would be of emptying this tank. So that's it for today's lesson on work. Hopefully you've enjoyed the video and learned something. If it's helped you out, please like and comment as to what I helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. And yeah, I will catch you guys in another video.